Hello, welcome to this lesson on geometry, which I shall call the method of areas. Now, it's a very simple idea and very well known idea, but it gives us some wonderful basic theorems. And today we'll just go through quite a few nice theorems based on this simple idea. So, what exactly is this idea? It goes like this. It is something that you will be able to understand in no time at all. So you take a triangle and let's say that there is a line like this which divides the base in the ratio of, let's say, 2:3. Now it is very obvious that both triangle 1 and 2 share a common height. So for instance, if I were to draw the height from A to the base BC, this height is common for both triangle 1 and triangle 2. So if I find the ratio of the area of 1 divided by the area of 2, one quickly realizes that it is 2:3. And the reason is very obvious. This area is actually equal to half, let me just call it BD, half BD into the height, but the ratio of 2 is half BC into the height, and since they share a common height, this turns out to be 2:3. So that is all there is to this idea, but I think you will be in for a pleasant surprise when we look at the number of nice theorems and problems that this can solve. So let's get on with it. First of all, I shall prove Ceva's theorem, which is one of the really nice basic theorems, and it's a theorem which I shall now quickly state to decide on the concurrency of the so-called serients. So suppose I have a triangle and suppose I have a line that joins A to the base BC. It's called a seriant. Now if it so happens that we draw a few serients, and let's label them as X, Y, and the third seriant passes through the intersection of the first two serients. So in that case, we say that the three serients as shown in the diagram are concurrent. Now what is the condition for the serients to be concurrent? And I shall presently write it down. It is the so-called Ceva's theorem, and it goes like this. If Bx divided by Bx divided by Xc multiplied by Cy divided by Ya multiplied by Az divided by Zb is equal to 1, will be equal to 1 if the serients are concurrent. Now this is Ceva's theorem, and now I also state that the converse is true. So if this condition is satisfied, then the serients are concurrent. So this is the Ceva's theorem. As you can see that there is a nice symmetry even in the statement, and now the proof is very simple and it uses the method of areas, and there is a lot of symmetry in it that you cannot miss. So now I shall write down the proof, and it just involves a little bit of algebra. You've got to be a little patient. It's actually very simple and very neat. So let me see if I can do it as neatly as possible, and I shall just draw the diagram again. So like I said, we are going to use the method of areas, and let me just draw the three serients now which are concurrent and label them as before: A, B, C, X, Y, Z. So let me tell you the first step. The first step, let me just call this as O. The first step is something when I write it down, you will quickly realize that there is no problem in accepting it. The area of ABX divided by the area of ACX. Now one quickly realizes that it is equal to BX divided by XC. Now this is also equal to this triangle area divided by this triangle area, and for the same reason, the method of areas, this shall not require any further explanation. OBX and OCX. So far we haven't had much trouble in writing down these steps. Now we should use a simple algebraic rule. If A by B is equal to C by D, then the ratio is also equal to A minus C over B minus A. This simple algebraic manipulation is the next step, using this equals to this, and the fact that they are both equal to this we will use in the end. Now let's focus on this and use this algebraic manipulation. So this ratio is also equal to ABX minus OBX divided by area of ACX minus area of OCX, and we're almost done once we realize that the area of this minus the area of this is just this area, and here is where the nice symmetry comes in, divided by, we should use white, by this area. Now you can see that this is going to be a cyclic repetition very soon, but you can see that this wing divided by this wing is what we are saying. So this subtraction leads to the area of ABO divided by ACO. So finally ABO, which is the yellow area, divided by ACO, which is the white area, is equal to BX by XC. Now I shall quickly jump to the next two steps using the symmetry of this relation. Please watch this. It's fairly nice, easy to predict. Now what I'm going to do is go ahead in a cyclic fashion and find the ratio of this wing to this wing, and you easily predict what this ratio is, but let me just write it down first. Area of BCO divided by the area towards its left, which is area of BAO, is obviously equal to, by symmetry, CY divided by CA. And you can see how we are getting inching closer to Ceva's theorem quite easily. CY divided by YA. And we can write down the next relationship as well. Let me see if I can get this right. It is going to be, okay, this ratio, very easy. This wing divided by this wing. So let me write it down carefully. Area of CAO divided by the area of the wing towards its left, which is area of CBO, is obviously equal to AZ divided by ZB by the symmetry of the first relationship. So AZ divided by ZB. And once we have the three relationships, like symmetric and beautiful relationships like this, you know what is the final step. It's too easy to predict. So I'm just going to write it down now. It should be fine. We just have to multiply this with this with this and hope that everything gets cancelled and we get 1, which is a statement of Ceva's theorem. So there's the last step. We're almost there. Bx by xc multiplied by az by zb multiplied by cy by ya is nothing but bco divided by bao multiplied by CAO divided by CBO multiplied by ABO divided by ACO. I'm hoping that they all cancel out each other. Indeed they do. This one will cancel out with this, and this one cancels out with this, and this one cancels out with this, and I can heave a sigh of relief. This is 1 and we are done. As you can see, this is a very nice and simple idea of the method of areas, and we get this wonderful powerful theorem which can help us to prove concurrency. Actually, to prove concurrency, yes. So that what we're really going to use is the converse of this. It's a proof by contradiction. I shall leave it to you to get to the book Geometry Revisited and do that as well. Now we're not done with this method of areas. It's going to give us a few more gifts. So let me get on with one more extraordinary result, extraordinarily simple and extraordinarily nice. So here we go, and they are related. So the first thing is we will prove using what we just learned called Ceva's theorem that the medians are concurrent. And that's a nice relationship. Now what do you mean by the median? We mean that x is the midpoint of BC, and we mean that y is the midpoint of AC, and it's not obvious that the third median also passes through the same point, which is famously called as the centroid. Now why is it that the three medians are concurrent? It's very nice. You can see here that Bx divided by Xc is basically 1 multiplied by Cy divided by Ya is also 1 multiplied by Az by Zb is also 1. So this is definitely equal to 1, and by the converse of Ceva's theorem, which we haven't proved, that medians are concurrent. But let me now do one more interesting thing, which is to prove that the point G, the centroid, a well-known result, is dividing the median in the ratio of 2:1. So what we are saying is, maybe I should just get rid of this. What we are saying is AG divided by GX is equal to 2/1. Now we're going to give a very simple proof using the method of areas. So here's what we're going to prove first. It's not going to come that easy as well. We just have to be a little patient here. Now, the first step is a very neat result, which is that all these areas of all these triangles are same. So obviously they are not congruent, but the areas are same, and yes, we are going to use the method of areas to prove that all the 6 areas are same, and that looks very interesting. So let's start. Now it is quite obvious by the method of areas that the area of these 2 triangles are same, and the reason is that x is the midpoint of the base. So if this area is x, then this area is also x. Now by symmetry, for the same reason, these 2 triangles have the same area, and these 2 triangles have the same area. And now as a final step, what you have to notice is that this triangle and this triangle have the same area because x is the midpoint, and that would mean that 2z plus x is equal to 2y plus x, and that would mean that z is equal to y. So we can now change this to y and y because z is equal to y. And as a final step, you can see here quickly that x has also to be equal to y because the area of these 2 triangles is equal, and that means that x is equal to y, and you can also write this as y and y. I'm not writing the obvious steps. We have proved that all the 6 areas are same, and now we'll come to this. And this also is by the same logic, the method of areas. So let me write down the final step. Now here you have to consider, maybe I should use a different pen for the last final assault. You need to consider, let's say, this triangle and this triangle. Now we should choose C as the vertex from which you have to draw the height. Let's say this is the height or the perpendicular drawn from C to this base AX. Now the thing to note is that this height is common to this triangle as well as this triangle. So we're almost there. The area of ACG divided by the area of CXG is equal to, as you can see from the picture, 2y divided by y, that is 2y divided by y, that is 2:1. But then again, by the method of the areas, because of the common height, this ratio is actually equal to AG divided by GX, and we have proved the important relationship, that is the centroid divides the median in the ratio of 2:1. And you can see how quick and neat was the kill, and by a very simple idea called the method of areas. Now we're still not done. Let's do one more very famous and very popular result using the method of areas. So here's the result, very famous basic geometry result, and let's do that as well before we finish today's lesson. Now this is also going to be very nice and simple to follow. So here's the relationship. So suppose you have a triangle and you have an angle bisector. Let's say you have the angle bisector of, so let's use the, okay, this is the angle bisector of A. So these two angles are same. Now if we have an angle bisector of A, and let's call this as D, and suppose that this ratio is m is to n, and this side we call it as C, and this side we call it as B. That is the standard notation. And now I repeat, if AD is the angle bisector, then C by B will be equal to m by n. Now I want to give two proofs of this very nice and neat result. So I repeat, if AD is an angle bisector, then C divided by B is equal to BD, that is m divided by n. Now let's do two proofs of this theorem. The first one will be the method of areas, and so let me just do the method of areas proof first. For that, what you have to do is drop a perpendicular from D and do the same thing on this line. Now, by the very popular angle bisector theorem, we know that these two sides are same. Let's call this as H and let's call this as H. Now the reason these two sides are same is because B lies on the angle bisector of A. We're almost done. All we need to do is, what is the ratio of this triangle to the ratio of this triangle? So the ratio of the area of this triangle to the ratio of the area of this triangle by the method of areas is equal to m by n. Okay, so let me write that down. The ratio of the triangle of ABD divided by the ratio of the triangle of ACD by the method of areas that we just discussed is equal to m divided by n. And the reason is that these two triangles share a common height if you draw it from A. But now you realize that there is another way to write the area of this triangle, and that is half C into H. And the other way of writing the area of triangle ACD is half base, which is B, into this height H. And we quickly see that this is equal to C by B. So m by n is equal to C by B, and we are done with another very nice but basic result of the geometry of triangles. So this is true if AD is the angle bisector. I think this has been a long lesson but very easy lesson and very nice theorems. We will do some interesting problems to use these ideas in the next class. I hope you will log in. Thank you very much. Bye.